We previously learned about the structures of monosaccharides, including the open chain form and the hemiacetyl or cyclic form. And also in an earlier unit, we've learned about oxidation reactions of alcohols and aldehydes. And we've also learned about reduction reactions of aldehyde and ketone groups. These functional groups all appear in monosaccharide molecules, and so monosaccharides, as a result, are subject to oxidation and reduction reactions, which we are going to focus on in this video. By the end of the video, you will understand what groups within monosaccharides are subject to oxidation and reduction reactions and what implications those reactions have toward the function of those particular molecules. The reason why in this beginning screen I show a blood glucose test is because these oxidation and reduction reactions are critical toward the ability of this type of blood glucose test to function in quantitatively measuring the amount of glucose present in a person's bloodstream, and hence being useful for determining whether a person has elevated glucose and very helpful in monitoring diabetes. So let's take a closer look at oxidation and reduction reactions. We're going to focus first on oxidation reactions. So we're going to head this oxidation of monosaccharides. And we're going to start with some throwback material here to remind us about what types of functional groups are suitable for oxidation. The functional groups that we previously talked about with regard to oxidation that also appear here in the monosaccharides unit are, in the monosaccharides unit, we see aldehyde groups commonly appearing in the open chain forms of monosaccharides. Those were referred to as aldoses because they have an aldehyde group. We saw ketone groups appearing as well in ketoses. And additionally, we saw alcohol groups aplenty within the monosaccharide molecules. Now, as we think about oxidation of these types of molecules, of the three types of molecules that we see here, aldehydes are the most readily oxidized of the three functional groups. Ketones, on the other hand, are at the opposite end of the spectrum. They're not generally oxidizable. Alcohols fall in the middle. They can be oxidized, as we learned in earlier units, but they're not as easily oxidized as aldehydes. When we previously talked about aldehyde oxidation reactions, we saw that in aldehyde oxidation reactions, what would happen was that the aldehyde functional group, which I will draw here and draw a squiggly line to represent whatever that aldehyde group is connected to in the rest of the molecule, that when the aldehyde underwent oxidation, which I will abbreviate with an O in brackets, that aldehyde functional group was converted into a carboxylic acid functional group, COOH. And so within the realm of monosaccharides, the oxidation of the aldehyde group is going to be the most common oxidation reaction that we will encounter, and the one that is most relevant biologically and in terms of biomedical testing. When we look at aldehyde oxidation of aldehydes occurs within the open chain form of the monosaccharide molecules. The reason why it appears in the open chain form and not the cyclic hemiacetyl form of these molecules is because in the hemiacetyl form there is no longer an aldehyde group. Instead, it's been replaced with a hemiacetyl group. So when we look at oxidation, we're focusing on the open chain form of the aldehyde groups, or of the aldohexoses or aldopentoses, or whatever type of aldehyde-containing monosaccharide we are dealing with. And as an example of that, if we take D-glucose, we have our aldehyde group at the top in a Fischer projection. The Fischer projection shows the 6 carbon atoms in a vertical orientation here. I have inadvertently made that very last bond here at the bottom quite long, but it works. So we have our carbon atoms here, 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 and here represented by the intersections of the lines. I'm going to fill in the OHs and the Hs to represent the exact stereochemistry of this particular molecule. This is D-glucose, so I've put that final chiral center OH group on the right there. Now filling in on the left side of each of these carbons with whatever is needed there, be it H or OH, to finish this off here. and this is the structure of D-glucose. I do not expect you to have memorized this structure. Instead, what I expect is that you're able to look up this structure and apply it toward problems. So in the case of D-glucose, if D-glucose is treated with an oxidizing agent, I will abbreviate that as O in brackets for now, what's going to happen is that the aldehyde group, being the most easily oxidized group within the molecule, is what is going to be targeted by the oxidation reaction. So that aldehyde group, CHO for short, is going to become COH, a carboxylic acid group. The rest of the molecule will generally remain unchanged because we react only the most reactive portion of the molecule. The most reactive portion is that aldehyde group. The aldehyde group is the most easily oxidized of the functional groups there. So we're going to leave the alcohol groups all intact because those are less reactive than the aldehyde group. The aldehyde group is what gets oxidized in this reaction to form the carboxylic acid that I'm highlighting in blue now. In this particular reaction, one way to carry this out is by using an oxidase enzyme. Oxidase enzymes are enzymes that catalyze oxidation reactions. So I'm going to plug in here oxidase. And what the oxidase will use is oxygen as the source of the oxygen atom needed to convert the aldehyde group into the carboxylic acid. It also uses water as an additional reactant here. Both water and oxygen are abundant. And this is what will catalyze the reaction, is specifically this oxidase enzyme. And the really cool thing about this particular reaction that I'm showing you here is that this reaction is the basis of the chemistry behind at-home blood glucose tests. So in at-home blood glucose tests, embedded within the test strip is the oxidase, which comes into contact with water and oxygen from the environment and from the blood sample. So this is what's in the testing strip here for blood glucose testing. And so when glucose present within the blood comes into contact with the oxidase in the presence of oxygen and water, which are abundant, what's going to happen is that the aldehyde group gets converted into the carboxylic acid group. So you might say, well, can we measure the amount of this product molecule here, perhaps as a way of measuring how much glucose was in a person's blood? Well, that doesn't work very well because there's not really a good way to detect with specificity either of these molecules or most other monosaccharides or disaccharides for that matter. But what is readily detectable is a molecule called peroxide, H2O2. And that just so happens to be a byproduct of this reaction. When we react our D-glucose with oxygen and water in the presence of this oxidase enzyme that catalyzes the reaction, a byproduct of the reaction is peroxide. And so what happens in the at-home blood glucose test is that the blood glucose test actually detects the accumulation of peroxide because the amount of peroxide that accumulates is proportional to how much glucose was started there. So the H2O2 is what's actually measured in the test. And the reason why that works is because the amount of that peroxide, H2O2, that's present is going to be proportional to the amount of glucose that was present, thereby allowing us to establish the concentration of D-glucose that was present in the blood to start with. Now let's move along and talk about reduction of monosaccharides. We're going to go back in, like we did with oxidation reactions, and think about the three types of functional groups that we see in monosaccharides. Those three main types of functional groups are, we see aldehyde groups, we see ketone groups, and we see alcohols. As we think back to which of these functional groups are subject to oxidation, or I should say in this case reduction reactions, aldehydes can be readily reduced, and specifically they're readily reduced to alcohol groups. So in other words, if you take an aldehyde, treat it with a reducing agent, the product will be an alcohol. Likewise, ketones are also readily reduced to alcohol groups. In contrast, alcohols are not generally reducible. And so, when we look at monosaccharides, we target, in reduction reactions, the aldehyde groups and the ketone groups. Aldehyde and ketone groups are present in the open chain forms of monosaccharides. So these reduction reactions, we focus on occurring in the open chain form of monosaccharides. Because in the hemiacetal form, the cyclic form, instead there's a hemiacetal group in place of the aldehyde or ketone group. So let's take a look at a really cool example of a reduction reaction. And that is in the molecule D-glucose, which we saw before appearing in the oxidation reaction. D-glucose is, of course, a common, very abundant, very biologically essential structure, and so we focus on that quite a bit here. I'll draw the structure of D-glucose, and again, I don't expect you to have memorized this structure of D-glucose. What I really want you to be able to do is apply that toward problems like this, where you apply the knowledge you have of chemical reactions that you've gained throughout the semester here, and use that to solve problems related to the concepts that we're learning. So D-glucose, if we treat that with a reducing agent, for example, sodium borohydride NaBH4 was a specific reducing agent that we looked at previously. What's going to happen here is that an aldehyde group or a ketone group, whichever is present, it'll be one or the other. It'll be an aldehyde group if we have an aldose. It'll be a ketone group if we have a ketose. When we treat that with a reducing agent, what's going to happen is that the aldehyde or ketone group gets converted into an alcohol group. And so in the case of aldehydes, like we learned back in our previous chapter on aldehydes and ketones, when aldehydes are reduced, they form primary alcohols as the product. So we'll go ahead and draw in everything as it was to start with the exception of our aldehyde group becoming a primary alcohol group. Drawing in the rest of my H's and OH's on each of these carbon atoms here, as we need to do here. And in this reduction reaction, our product now has CH2OH at the top at position number 1 of the chain, rather than an aldehyde group, because we've treated with a reducing agent such as sodium borohydride. So how is this reaction biologically relevant or commercially relevant? Well, the artificial sweetener industry is a multi-million-dollar industry. The search for zero-calorie sweeteners goes quite far, quite wide, and goes quite a ways back historically. There is a tremendous amount of demand for that. And one approach that's been taken to develop artificial sweeteners, sweeteners that taste sweet to the taste receptors on the tongue, but are not recognized by metabolic enzymes and hence pass through the digestive system without providing calories. These reduced molecules, sometimes, not always, but in some cases, provide a sweet taste while not providing caloric benefits. And so, as a result of this, in the case of D-glucose, what the reduction product of this is called is D-sorbitol. And D-sorbitol has indeed been used as a zero-calorie sweetener, as a key application of the reduction of D-glucose. So, with that, we can use reduction reactions industrially to convert aldoses, such as D-glucose, as well as ketoses, into the reduced form of these sugars, which sometimes still retain their sweet properties, but no longer have the ability to be metabolized. Also, you will notice that after the molecule has been reduced here, it's no longer able to form the cyclic hemiacetal form because of the fact that it has no carbonyl group here in order to allow that reaction to take place.